Good afternoon to all. We are on the fourth day of this 5 days machine learning program. And previously, if I try to recap, we started with the remote sensing lecture in that defining image properties, platform sensors, and so forth. Then we talked about journey from basic machine learning to presently different algorithms people are using, people have developed. Then parallelly there was a lecture on Python for machine and deep learning algorithms. Then I covered fuzzy algorithms and the issues in them, plus the temporal data, how to process temporal data, specifically with the fuzzy algorithm and with a lot of applications for mapping a specific crop. It can be paddy transplanted fields, burn paddy fields, sunflower fields with different stages and so forth. So today we have reached to the first lecture, starting by me on neural or network-based learning algorithms, ANN to CNN and then RNN. And today the second lecture will be on different models for detection purpose as in guest faculty. So let's start with this first lecture today now. So this network-based learning algorithms, basically people are trying to mimic like human brain. So here you can see the neural network. That this is a very basic algorithm. Previously this was called very advanced algorithm, but nowadays relatively when the deep learning has came and it has developed the different models, so which are based on neural network. So neural network has become as base algorithm in the deep learning domain. And here if you try to see the neural network, it is a broad class of models that mimic functioning inside the human brain. There are various classes of neural network models depending upon what is the problem and how to classify. So we can have different classification of ANN models. There are different form each other depending on like what problem, if we see what problem ANN can tackle. So we can have classification like for prediction purpose, for classification purpose, and for clustering purpose. What is the structure of model? So that is second parameter to classify ANN types. So there can be different structures to handle the different problem. So it is not a straight mathematical expression. We have to create the structure where different functions are integrated in the form of neurons, where the functions are kept and they are interconnected. The third parameter for classification of ANN type can be model building algorithm. Model building algorithm means training of neural networks. So what are the learning algorithms we can use to train the neural network? Here you will see the well-established training algorithm is back propagation neural network, which is following with the concept of feed forward. So training data is a feed forward, and with the back propagation approach, we can train the neural network. And these neural network, mainly we can use it for prediction as well as for classification problems, obviously in supervised mode. So there can be unsupervised ANN models, but they are very specific. So it's unsupervised ANN models are different and supervised ANN models are different. Same model, you cannot use it in this domain as supervised or unsupervised. Previously, like you have seen, statistical based algorithms or fuzzy based algorithms, same algorithm you can use it for as a supervised mode or unsupervised mode. But here, when we have to use supervised or unsupervised mode neural networks, so we have to see which model can be used as supervised and which model can be used as unsupervised. Here we can see some of the biological components, and then we'll try to compare and correlate with the mathematical neuron. So most important functional unit in human brain is called neuron. So this is the smallest unit in the human brain, smallest cell called neuron, and it has different parts like dendrites, which receives the information from the environment. Then it has cell body, which does the which receives the input, plus it does the processing of the data. Then there is axon, which carries the processed information to other neurons. Then there is synapses, which basically gives the junction between axon and dendrites of other neurons. So synapses basically they gives the joining the two neurons, and like this they make the network. Now if you compare this biological neuron components with the mathematical one, you will see definitely that all these components are present in the mathematical neuron also, where you have dendrites to receive the information, cell body to process, axon to connect the neurons. And here we'll see one example with a single perceptron. So there are different terminologies. When we talk about perceptron, single perceptron, that means we have a single neuron, and in that all the inputs are coming, and that does the processing. But single perceptron cannot give you full solution. That's why people go for network of perceptron, and that is your artificial neural network. Here if you see the data, in this case the data is p-dimensional, right? For each input of the data there is weight, like W1 to WP, and what the input goes to the cell. So this is your cell body. So inside this the input is going weighted sum I. So weighted sum is your like W1x1, W2x2, and so forth, WPXP. So this weighted sum is going in the cell. So cell has basically two parts. The first part stores the weighted sum, and second part does the processing. So how the processing is done with this function? So output is equal to, output is a function of Fi. I is your weighted sum. So here V is the output, which is a function of Fi. Now here you can see some of the things in this perceptron, and it receives input like your X1, X2, XP from other neurons or from environment. If I'm talking about this neuron, so this neuron may be receiving output from the environment. This neuron may be receiving input from the environment or from previous neurons. This input is fed in through connections with weights. So here you will see each weight are connected. Each input is connected with having some weight. So weight value is always there at each connection, and by this we can find out the total input, and total input we can quantify is equal to weighted sum of inputs from all sources. So at a given neuron, whatever input is coming, that is multiplied by the weight, and we calculate the weighted sum as an input to the neuron. Then the neuron has transfer function, or very basic term is activation function, which converts the input to output. And since function is non-linear, so your output has non-linear behavior, and output goes to other neuron or environment. If your neuron is intermediate neuron, so the output will go to next neuron, and if the neuron is the last neuron in the network, then the output goes to the environment. Some of the transfer or activation function we can see, and it's very, very important when we are working with neural network. This is a non-parametric approach. ANN, if you see, it is a non-parametric approach. Why? Because there are so many parameters, and these parameters should be tuned, right? And we cannot just estimate, and if you found for a particular case study these are the parameter values, so same parameter value cannot be applied on other problem, that has to be further adjusted. So these parameters are free. We'll see what are the all parameters in the coming slides, but ANN is called non-parametric algorithm. So here if we see transfer or the very common term activation function, it can be 10 hyperbolic, So this is a mathematical expression. The input is here, minus infinity to plus infinity. Output is minus 1 to 1. So in this function, the input can be minus infinity to plus infinity, but output will remain minus 1 to 1. If you take logistic one, this is also quite common. Here input is again minus infinity to plus infinity, but output will be 0 to 1, any value. Sometimes people apply threshold, which is not so common to apply, to consider to apply in ANN model, but when we want to just decide or apply the addition rule, so that way sometimes people use this threshold activation function also, where you can put a condition: if x is less than 0, output is 0. When x is more than or equal to 0, then the membership value is, output from that neuron is 1. So here it will give you two output, either 0 or 1, nothing in between. We can see now basic structure of ANN, and that will give you more feel if people are new to understand how the ANN works. So here, if you talk about neural network, it is basically neurons form a layer. So a collection of neurons, here you can see 4 neurons are making one layer, and this is your ith layer, input layer, where the input is coming x1 to x4, and this input directly passed out from the neuron. There is no processing at the input layer actually, so this you should note down. And after that, you can see in the one more layer, output layer, we can keep minimum 1 neuron, and we can have more than 1 neuron also. It all depends. If we are expecting less number of class, we can keep just 1 neuron. If we are expecting large number of classes, then we can keep 2 or more than 2 neurons. That is because we have to fix the target value, and if I'm taking the logistic function, my output is 0 to 1, and that range is quite small. If I have to extract 10 classes, so for 10 classes I require separately 10 target values within 0 to 1 range, which is quite small to select the 10 values. So that way, if I take 2 neurons, my output always will be 2-dimensional, and then I can play permutation combinations, and with that I can have more number of outputs from the neuron. So that way we decide the number of neurons in the output layer. It does not affect the accuracy of the output. Then in between you can see there is a hidden layer starting from 0, and here you can see the connectivity. This is connected here, this is connected here, this is connected here, and this is connected here. Like this, all 4 neurons are connected to this neuron. Here, this is connected here, this is connected here, and this is connected here. Same way, other neurons of the next layer is also connected. Direction of information flow is from here, input to output. So this way, the direction of flow takes place. And each connectivity between 2 neurons, there is a connectivity, and each connectivity will have small weight value. It is compulsory. If it is not assigned, we can assign randomly. Then we can see some logic about hidden layer. How many hidden layers we can keep? We can keep none hidden layer. So this is your output layer, and this is your input layer. So there is no hidden layer here. In the second case, we can have one hidden layer with 2 neurons. That is a hidden layer size. Hidden layer size means number of neurons in the hidden layer. We can have 2 hidden layers, each having 2 neurons. So there is no standard rule. We can find out by what combination of hidden layer we can get the best output. So that way we decide the hidden layer. So which structure giving the best accuracy, that will decide the hidden layer. Then we can see a couple of things to be noted down when we are creating the neural network model. Here, connecting the neurons of the same layer is not allowed. So we don't connect the neurons of same layer. So this is not allowed. This is not allowed. and here also not allowed. Second thing, jumping is not allowed. You cannot connect this neuron here. That way the structure will not give you the good result. So these are the few things to be noted down while connecting the neurons. Then if you see here particular ANN model, it is not a mathematical expression. You can simply say ANN model is Fx equal to V. So you cannot represent a state like this, because this is ANN model is not a mathematical function. We join the different functions with connectivity, with weights, and that way we create the ANN model. So here what will happen, according to my input data, if data is your three-dimensional, so this is my input data, we can get the output Y if it is single neuron, and I can take the activation function here or transfer function. So here however it is characterized the ANN model, like it has an input neurons, it has a hidden layer. So we can try with hidden layer, maybe starting from 0, then one hidden layer. Neurons in each hidden layer has to be decided. Then output neurons, and how much neurons will be there in the output layer, and the weights for each connection. So once we do it, we can say fitting ANN model means specifying the value for all these parameters. So for all these parameters, if I decide the values, then we can say model fitting is done. So here you can see some more about the model. If my data is three-dimensional, so my data will be like this, one dimension from each band, and each data is one dimension data is going to each neuron. Here x1, here x2, and here x3. Then this is the activation function, which is kept here in two parts. First part is the weighted sum of the input, and here is your function fx, and these are weights for each connectivity. The small weights are attached, not very large value, because if you keep the large value, your activation function will get saturated. I've shown you the activation function. I can repeat here again. This function I'm talking about here. So this function should not get saturated. If you see practically around +8 and -8, below -8 and beyond +8, the function is getting saturated. It will give more or less same output. So we have to see my values, input values with weight values should not be very large. If they are large, they will start choking the. If the values are large, what may happen? The basically function may get saturated, right? Practically, you can see if your value is say more than 10, more than 8, +8, and less than -8 in the input, your output will be tending to 1 or -1. So you cannot discriminate when your input is 100 or 1000, output will remain same, to be around tending to 1. If your input is -100 or -1000, your output will remain to be -1. So function cannot discriminate the output. That's why we have to scale down the values, the input values, so that my output is always within the limit of activation function. So we can see what's the limit. For 10 hyperbolic, it is -1 to 1. For logistic, it is 0 to 1. So here I was talking about, now you can see in the model, as per my data is three-dimensional. So input neurons will be 3 and output neuron will be 1, for example. Minimum 1 I have taken. So these are the fixed parameters depending upon the input data. These are the free parameters like hidden layers. How many hidden layers we have to keep? Here we have kept one hidden layer. Then hidden layer size, that means how many neurons we want to keep in the hidden layer. And then weights to be specified, because there is connectivity in the ANN model, and for each connectivity we have to decide the weight value. initially there is no weight, so randomly we can assign, and later on during training, what happens, the meaning of training means adjusting the weights. That's the main objective. So whatever weights were assumed initially, these weight value can be adjusted during training, but the weight value should be small. They should not be very large, because finally we have to calculate weighted sum, and the weighted sum value should not be very large. Then we can see the real life example with the sample training data. Suppose this is training data from 3 band per class water, and this is a model already created with weight values assigned. Then you can see this is your weighted sum at this point, and if this is the activation function, output is 0.55. So we can see we have decided input, we know the output, and output is one dimensional, and this is the activation function. So here you got the weighted sum for this neuron. It was 0.2, and when 0.2 was fired in the activation function, we got output to be 0.55. So this becomes output, and same way for this neuron, this is weighted sum 0.9, gone in the activation function, output is 0.71. So these outputs from the hidden layer are working as an input to the output layer. There are weights assigned, so we will have weighted sum here, and after weighted sum we can calculate the output while passing the weighted sum in the activation function. So output is 0.478, but for this class of water we have given some symbolic output as a numeric symbolic output to be 0.5, but my output came 0.478. Then you can find out the error or predicted error, which is coming 0.022. If it is not acceptable, then we have to do training, right? Target value, you can understand, like I always give very funny example. If like when there is a newborn baby, and after a few days there is some function to assign the name or give the name to the baby. So once the name is given, all the relatives starts speaking that name to that kid, so that the kid should recognize. But when the first time that name is spoken, kid does not know, does not give any response, because the mind is not trained to listen that voice, and that's why kid does not give any response. But with the time, when continuously the relative's mother goes on speaking that kid by the name, and after a few hours or few months or few days, the kid start recognizing that this voice is basically my name. So when the mother was speaking first time by the name to the kid, kid does not give any response, but mother wants some response. The response can be moving hands, moving legs, rotating the body, or smiling, or blinking the eyes, and so forth. So that is the response, and that response is basically 0.5 numerically here as a target value. So mother fix some target value, suppose 0.5, in the form of the movement of body parts I am talking about here, and here we are talking about the numerical value. So that's the target value. And if I compare, mother compares the output response from the kid by the target value fixed by the mother, and that difference, if it is very high, he or she speaks again the name. So that, and that process goes on number of times, and due to this iterative process, the kid starts recognizing that this is my name. Same way here, when we get the output 0.478, which is giving very large difference as a predicted error, so this error has to be reduced through training. And reducing the error means adjusting the weights, because weights are culprit, they are assumed, and the assumptions are not always correct in life. How to build the model? Whenever you think to use ANN model, question comes how to build the model. So we have to see here first dimensionality of the input data, then we can decide output if number of classes are less, just one dimensional. If the number of classes are more, we can take more dimension of the output. The activation function we can fix, and we have suppose input 3-dimensional, output 1-dimensional. So we can decide the hidden layer, how many hidden layers, and the hidden layer size, right? So there is no strategy. You have to go for trial and error method. Then how to get the weights, there is also question mark for each connectivity. So we can decide it through assumptions. We can assume the weight value initially for each connectivity, and then we can do the training data. So we can have the training data of each class, we can fire it and get the output, compare with the target value, and if the error is large, we can train, right? So here this is the error to be calculated, and this should be minimized. There is one more terminology. At each neuron we have to keep the bias. So bias has unit input with some weight value, so that also has to be assigned, but input is always unit value. So the role of bias is that ANN should not stuck up somewhere at any stage. Number of times that model may encounter 0 value, and due to that model may stuck up in a loop. So to avoid it stucking up the ANN model, the bias is introduced at each neuron. The characteristic of this bias is input of this bias is unit value, and there is some weight value. So here, how to train the model? Start with a random set of weights. For once we create the connectivity, then fill the weights for each connectivity randomly. Then take the training data, get the target value, compare the target value with get the output value, and compare this output value with the target value. So this is your target value, and this is your output value. If there is an error, and if this error is not acceptable, then we have to reduce this error during training. That means reducing error means we have to adjust the weights so that this error is reduced. So network fit the first observation value. Now once this is done, we can again fire the second observation. That means same training data we can fire, get the output, compare with the target value, check how much is the error. If error is not acceptable, again repeat. So like that we have a cycle, and we go on doing number of times the cycles repetition, and check finally the error, it is acceptable or not. If it is not acceptable, we can go on iterating number of times to reduce the error so that error is acceptable. That means weights are adjusted. Bit more details on back propagation before we see mathematical expression of how this back propagation works. Each weight share the blame for prediction error with other weights. So back propagation algorithm decides how to distribute the blame among all weights and adjust the weights accordingly. The small portion of blame leads to a small adjustment. When the weight is contributing less error, that weight require less adjustment. The weight which is contributing more error leads to large adjustment. So large portion of blame lead by the weight leads to large adjustment of that weight. So this is the theory behind how the weights are adjusted. Mathematically, we can see here this is the output coming from the output neuron, and this is the target value. So using these, we can get the error at the output, right? And if this error is not acceptable, we can adjust the weight. So how to adjust the weight? We can adjust the weight like this: delta W is equal to eta. It is a weight constant called learning parameter, learning coefficient, and delta J is basically your error at the output layer, and this is the input from each neuron at the output neuron. So that way we can find out for each weight how much adjustment is required. Once we know the adjustment of each weight, we can take this adjustment factor with the previous weight value, and like that we can find out the new weight value. So this can be done for output layer, and this can be done for hidden layer. So in the hidden layer, at the hidden layer point, we find out the error at each neuron of the hidden, and once knowing this error, we can adjust the error again from this factor. We can find out the weight adjustment factor of the weights which are between hidden and the input layer. So this way, the mathematically we can adjust the weight. There are few more parameters we can add. So here you can see the eta is a learning rate, which decides by what rate the ANN should learn. That means adjust the weight. Higher eta value, which is provided by the user for the complete model, and at the beginning, so learning rate will be more. It will adjust the weight more faster. If the learning rate is small, it will adjust the weight slowly. A second parameter also comes called momentum. So weight update rule can be modified so as to depend on the latest iteration. This iteration, and we have the following, like here, if the next iteration is n+1th for adjusting the weight value, so this adjusted weight value at nth+1 iteration is equal to weight adjusted at nth+1 iteration, that is eta, error at the output plus the input coming to the each neuron plus alpha. Alpha is again one more constant, multiply by the weight adjusted at nth iteration, that is previous iteration. So like that we can find out the actual weight adjustment at nth+1 iteration. Alpha is momentum, its value goes from 0 to 1 and it's called momentum. So the role of momentum in ANN is to increase the speed along a local minima and to increase the speed along flat terrain. Local minima means there are, for each class works as a, error at each class works as a local minima. So at particular class, it should not goes on reducing the error at particular class. It should consider the error at each and every class. That's the meaning. It should increase the speed along a local minima, and it should increase the speed along flat terrain. Flat terrain means when the error is not decreasing, it is more or less constant. It should increase the speed of learning. So these are two roles of momentum if we add in ANN. So overall, adjusting, we can see, decide network architecture through hidden layers, neurons in each hidden layer, decide the learning parameter and momentum, initialize the network with random weights, and then iterate from I is equal to 1 to n. So feed forward, fire the training data once, get the output, from output get the error. If error is not acceptable, adjust the weight. Once weights are adjusted, go to next iteration, fire the feed forward the training data, get the error. If it is not acceptable, adjust the weight. So again, fire the training data of each class like that. So this iterative process goes on, and you have to check for convergence. Once the error is acceptable, it will stop. Otherwise, it will go on doing iterative process. So this way, we can say the training algorithm of ANN works. So this in these slides, I just talked about what is artificial neural network compared with the biological neuron. Different components, mathematically and biologically, you can see they're quite similar. Then single mathematical expression of a perceptron, then mathematical model of a artificial neural network, its components, what we can do, what we should not do in ANN, what are the free parameters in ANN, and then training concept through back propagation mode, and having two more extra parameters, learning rate and momentum. Now from here onwards, we'll go for deep learning. So deep learning basis we'll cover, and so deep learning is basically a set of machine learning algorithms based on multi-layer network. Again, it is following more or less same concept like artificial neural network, where it has input, it has hidden nodes, and it has output. But the question comes, how we get the deep learning concept in a learning algorithm. The deep learning concept comes, please remember this, very, very important. Deep learning concept comes when we are extracting large number of features from a given input data. It is not increasing the number of layers. It is not increasing the number of neurons in the layer, which can give you deep learning concept. Deep learning concept comes when we are extracting large number of features through a convolution approach or through filtering approach, and that way, one way you can say the dimensionality of the input data is increased at the pre-processing stage, and that gives you deep learning concept. So it is not just basically increasing the dimensionality of the data, but extracting different features. If you recognize my first lecture and first slide, I was talking about pattern recognition, and they talked about the features of an object like color, shape, size. So all these features which are extracted from a given input data through convolution approach, and that gives you the deep learning concept. So here basically you can see we can train the ANN model, like cat and dog is a very common example. So we can train it for cat, multiple images of cat, multiple images of dog, and we can train it. And once the model is trained, and if I give an unknown image of cat, it can tell, yes, there is a cat in this image. If I give an input image of dog, yeah, this tells there is a dog. So that way the ANN is trained or with the deep learning concept, but mainly the train means the weights are adjusted to recognize that this input is cat and this input is dog. So that is the way this concept comes. Now we can have some learning taxonomy. It can be under supervised deep learning concept. There are so many models in the literature you can see, and some are still coming up because it's the growing topic last 5 years onwards. The first one is supervised convolutional neural network, CNN. Very basic deep learning concept, and it is used in different domain of deep learning concept in different ways. Modified versions is also available. And second is recurrent neural network, RNN, and it has two forms like LSTM and GRU. Then you can have unsupervised few models like deep belief nets, stacked RBMs, stacked denoising autoencoders, and sparse autoencoders. So these are models which are designed, used for unsupervised approach, and these are the models, basic models used as supervised. So as I told you in ANN, same model you cannot use as supervised or unsupervised. So what is convolutional neural network? CNN, it is a multi-layer neural network architecture. Again, it is a layer concept, multiple layers you will see. So here, this is the input layer or input image, and here from this image, using these, suppose 1, 2, 3, 4 feature maps has been generated. That means 4 convolutional filters has been applied. Here you can see the convolutional layer concept has been applied to get the 4 feature map. This image can be 2 band. So this image can be 2 band, but from 2 band you can see we are extracting 4 feature maps. So you can see one way dimensionality of the image is increased, but it is not just dimensionality, it is basically representing the image with more number of features as one layer. Then further basic steps, you can have subsampling. That means decreasing the image size through subsampling, like max pooling is very common. And then you can have average pooling. You can apply other median pooling also, which is not there in the literature, but you can test and see how they behave, and does they improve or does they give much better results. So this subsampling means decreasing the image size. It is again 4 feature map, and again further if I apply the convolution layer, from 4 feature map I am extracting 6 feature map. So again further dimensionality of the image is increased, and you can see image size is decreased through subsampling. That's called max pooling or average pooling, and so other poolings you can see from the literature, or you can design your own pooling concept for decreasing the image size. And then after that, in the end, you get fully connected MLP multi-layer perceptron. That's a ANN basically. So before ANN here, you can see there are pre-processing layers going on, mainly convolutional layer and subsampling layer. You may have multiple convolutional layer and multiple subsampling layers in the pre-processing stage, and then only after that, this processing stage, that the data goes to fully connected ANN, where the processing takes place and you get the output. So this is the basic concept, and here you have basically convolution layer with non-linear function. Here, if you see this one, this is a convolutional layer with non-linear function, like your activation function. I told you 10 hyperbolic, logistic, and so forth, to introduce the non-linearity in the data. Right after that, you have subsampling layer. So this is a subsampling layer, max pooling or average pooling. Then again, you have convolutional layer with non-linear layer. So here it is convolutional function or window or basically filter, and there here you have non-linear function also, which introduce non-linearity in the data further, and then you can have fully connected layers. So that way it is called supervised CNN model. So here you can see some component. This component is for feature extraction at the pre-processing stage, and this is for classification. Suppose if I'm using CNN for classification, so CNN is having two components. This is for classification, and this is for feature extraction. So this feature extraction makes the difference between ANN and CNN, right? So deep learning is coming when we go for large number of feature extraction from a given image. So once we extract large number of feature, then the deep learning concept comes. Nowadays, you can see these convolutional layer to be 32, 64, 128 we have explored. You may have after 128 255, and then you may have further 512 and so forth. So CNN, you can see some topology. It has feature map. So here you can see it as a feature map through convolutional layer, which is basically like as a layman you can apply low pass filter, high pass filter, and so forth. But they are not straight low pass, high pass filter. Just I'm giving you one example. Low pass or high pass can extract your edge detection and so forth. So feature means the different properties of the object are extracted and stored in the layer. And so here it is your feature extraction layer, and this is your shift and distortion invariance, or as very common term is subsampling layer. Next, you can see a little modified version of CNN as RNN, recurrent neural network. RNNs are used their internal state memory to process sequence of input. So it is more or less like in time series data, you can use it where you have sequence of input. Then applicable for tasks such as unsegmented or connected handwriting recognition or speech recognition. In RNN, all the inputs are related to each other. That means here you can see this is your input. You get we'll take all the questions in the end. Right, still for a few minutes I will talk about. So here the processing is coming up. Once you have the input output, some partially output is going out and some output is going back to the input. So it takes the output as input. So that way here you can see this output partially going to the further as an input to the next model of RNN. So it has sub models, and that's why it's recurring here. First, then again, this is taking the input, this is taking the output as an input, this is taking the output as an input. So that way the RNN goes. Some of the things we can see, like issues for large training data for learning algorithm. Like generally, if you see as per the experience, ANN may require little more training data compared to fuzzy based or MLC statistical algorithms. Here ANN for per class you may require 80 to 100 samples. Otherwise you cannot reduce the error what you want. That's the one. And if you talk about CNN and RNN, they require more large training data. It may go 3,000 to 30,000 samples. And that's why people talk about large number of training images are required. Question is where to get such a large training data, especially when we are processing remote sensing domain images. We cannot get 60,000 images of the same area. That is very huge. If you get one image itself for an area, that's more than enough. So generating chips as sample data for remote sensing may not provide homogeneity within samples. Again, if you see the training data in the CNN, like in 2D CNN or 3D CNN, which are quite complicated models, and they take the data as a chip form, small subsets. But if you come down and if you take 1D CNN data, so what happens? Your chip form data concept comes as a line data you can process, and the training data also comes down. But still, the training data for learning algorithm is quite huge. So question comes, how to get such a large training data? So what we have tried a concept to develop the techniques in which extension of samples from a few samples, like if we have 40 to 60 samples from a given image for a particular class, we can extend these samples to 3,000 to 30,000 plus samples. How we have done, you can see here as a conditional extension of training samples. Suppose this is your feature space and you have few samples from a class. So these green dots are the samples from a given class. So what we do, we have tried a function, and we can have the output as large number of extended samples. So you can see green are the seed pixels or seed samples from which we have extended the more samples as red dots as an extended samples. So from here we have extended few samples from 40 to 60 samples to 3,000 to 30,000 plus samples. So that way we can increase, if we require large number of sample data, we can increase this way. In lot of cases, we got very good results when we are increasing the training samples. Otherwise, if it is just thematic classification issues, like in remote sensing, we don't require so complicated models like 2D or 3D. With 1D model itself, we can work to extract the thematic map classified output. So we can go for 1D, and 1D does not require much training data. With our experience, with 50 samples or 60 samples or 70 samples are more than enough to get the good thematic map. Here you can see one comparative study we have done for a Formoset image, which was 4-band data, and we are able to get the output from FCM, PCM, the fuzzy based algorithms, ANN, MPCM, and then CNN. Here you can see from CNN output, if you compare with other outputs, the homogeneity is maintained. That means heterogeneity has been handled very nicely. So that is the one of the example of using learning algorithms. They handle the heterogeneity within class very nicely. But we have given one solution in the previous lecture, how to handle heterogeneity through the fuzzy algorithms. And there the fuzzy algorithms are quite easy to work, and they can handle the heterogeneity very nicely. We have done all these things through a GUI where we can apply CNN and RNN algorithms on a remote sensing data. We can display the image here, and we can create the training data. We can load the training data in the model. We can apply ANN. We can apply here CNN with just convolution layer or LSTM layer. This is for training, and this is for testing. We can apply different parameters like epoch, learning rate, hidden neurons, and so forth. So this is for CNN, where we have to decide the training data, threshold value, and epochs, training and testing. And here we can decide the your activation function like hyperbolic, rectified, linear unit, and sigmoid. And plus we can add the layers like convolutional layer, max pooling, and LSTM layer. If you want to add, if you want to take it like an RNN model, so you can you add the LSTM layers. If you want to work as CNN, just add the convolution layer and max pooling layer. You can add LSTM to make it hybrid CNN with RNN concept. So here, then second application of deep learning is through GAN, Generative Adversarial Neural Network based deep learning to remove cloud from optical temporal data. So here, what we have done, we have used GAN as a generative adversarial neural network with knowledge from pre or post nearest temporal image. So what we have done here, this is a pre-image of 27th of October, which is cloud free, but one temporal image what we found of 30th of October is having partial cloud. So can we remove this partial cloud and use this, make this image to be usable in the temporal domain? So yes, using from this information through GAN as a true input image and getting through generator the false image, and the false image is compared with this true input image, and then you can see this image has been generated from this image, from 30th of October image. This image has been generated. So here cloud has been removed, and we have made a 30th October image to be used in the temporal domain through GAN concept, because GAN is developed as a deep learning concept for transforming the images. You can see its structure. This is for generator to generate the false image, and to check, the discriminator will check the image is correct or not. If it is not correct, it will ask to regenerate, and it checks with the true image. With the real image, it checks the output. This is the model for generator unit, and this is the model for discriminator to check the image is correct or not. Then coming to very good application of deep learning for object detection, and there are large number of detection models like RCN, fast RCN, faster RCN, masked RCN, fused fully CNN, XGBoost, SSD, single shot detector, YOLO, you only looks once, and so forth. There are so many models which we have experimented for detecting the object, and not only detecting but using that detected information for classification. So here you can see one building concept. We have tried with the normal classifier, and we got false classification. Roads and ships were classified as a building, but when we have gone for detection approach through SSD, it was possible to detect the building through bounding box, and these bounding box information we have used to mask the building. And then once the building is masked, we have applied the fuzzy classifier within the box, and within the box only the building has been classified. And that's why here you can see the ships and roads has not been classified as a building. So we got very good results. So this is the application of detection and then classification. And that way, this is very good example for processing very high resolution images and basically extracting the buildings, because buildings are very heterogeneous information on a very high resolution image, and they get spectral overlap with other class for how to take care and how to tackle this problem. This is the one of the example. Next, we have tried to extract the brick links and sample image from Google Earth. So this is a bounding box, so we can detect. Then we have converted that as a point data, so we can have a point map of the brick links identified. And this is through mask, this is through SSD, this is through mask RCN model. And we can also extract the coordinates, geo coordinates of these brick links, so that we can identify on the ground, because these brick links are unauthorized activity, and these brick links at a time runs for 2 months for keeping the burnt ready bricks to be used, and for 2 months they continuously contribute a lot of polluted gases in the environment. So government can identify these brick links through these informations very quickly, and they may take some really serious actions for controlling the pollution coming out from the brick links, and for other sources also which are giving pollution to the environment. This is the one we have just experimented to identify the hangars at some airports. So you can see these are the hangars. So can we detect these targets? Yes, we can get the point data of these hangars, and we can get the coordinates. Then can we extract the aircrafts? Yes. up to model level, and we can get the coordinates. So these are all about, just I talked about ANN, then I moved to flavor of deep learning concept, the basic model CNN, then RNN, and then their actually structure, how they works, and then deep learning models. They are very, very important. And from deep learning itself, we have used the deep learning concept for masking the objects and then basically classifying and that it has a very good application for very high images. Their resolution is very high, so we can easily process the like buildings, roads, or trees very easily once they are captured through bounding box. And this is my last slide as usual. And thank you all for listening for this lecture from my side. This is a last lecture from my side, but now by 4 o'clock you will have one more lecture on deep learning, basically more detailed deep learning models, how they work and their applications.